Bismillahirrahmanirrahim. This is part F of lecture 4 on Descriptive Statistics and Islamic Approach. In previous parts of this lecture, we have been considering how to define inflation as it affects the budgets of consumers. In this part, we look at how economic theory defines inflation and how that leads to changes in the way that it should be measured. One of the central ideas of this course is that we cannot consider numbers in isolation from their application, and in particular how we compute inflation and how we work with it depends on the purpose of this calculation. Now, inflation affects the budgets of consumers, and that is how we have treated it in the past portions of the lectures. But there is another way to think about inflation, and that comes from economic theory. And economic theory gives us some different ideas about how inflation should be measured, and that is what we are going to study in this lecture. The basic starting point of economic theory definitions of inflation comes from the formula which is called the quantity equation or quantity theory of money, and that's very simply summarized as MV equals PT, money times velocity equals price times the number of transactions. There are two aspects to this formula. One is that it is an accounting identity. It just captures a relationship between certain quantities according to definitions. And the other is that it defines some causal relationships. It says that money affects prices. So these two things are separate and they have to be kept separate. The formula itself does not deliver us a causal relationship between money and prices, even though these things are often confused. We consider the quantity equation as an accounting identity. MV equals PT. Money times the speed of circulation of money is equal to price times T stands for transaction, where in transaction some commodity or service is being sold at a certain price. We can classify the monetary transactions which take place in the economy into two types. Some of these contribute to the GDP, while there are others which do not. There are different ways to do this classification, and details are complex, so we omit them from this introduction. The total amount of money used in GDP transactions over 1 year is just M star, where M star is money used in the first transaction, where Q1 quantity was sold for P1 price, and so the product is the money used in that transaction. And in the second transaction, quantity 2 was sold for price P2, and so the money used for P2 times Q2. We just take all of the transaction, thousands, millions of them, and we just add all of the money that was used in each transaction separately, and we get the total amount of money used. And these transactions are all the ones that contribute to GDP. So M star is equal to P1 times Q1 plus P2 times Q2 plus Pn times Qn, where n will be a very, very large number, all of the transactions in the whole economy for the whole year. Now this M star is not the same as money, because money will be used over and over again. So we need to look at the V, which is the velocity of money, which is how many times one piece of money is used. And so basically the total amount of money multiplied by the number of times it is used is equal to M star, which is the actual amount of money used in all the transactions. So if we just let Q1, Q2 to Qn, all of the quantities of all of the goods, we add them up, and we create a composite good. And that is that composite good costs M star, if we think of it as 1 unit, then 1 unit of this good, which is all of the commodities sold over the entire year. This is just one good, and it costs M star, the total amount of money that was paid for it. It is useful to introduce dot product notation. So if we have P is a vector of prices, P1, P2 up to Pn, and Q is a vector of quantities, then we just add the price, multiply the prices by the quantities and add everything up. This is called the dot product. In Excel, if you have two columns, one column has the prices and the other column has the quantities, there is actually a formula called the sum product. So if this table is in Excel columns from A1 to A6 and the second one is from B1 to B6, if you say sum product of A1 to E6, A1 colon A6 comma B1 colon B6, then Excel will multiply the prices by the quantities and add up all of these. So this is the easy way to get the price times quantity, which is the total that we need for these calculations. We've already discussed this in previous lectures, but we review this. How do we calculate a price index? We determine a quantity, which is a set of amounts purchased in the base year. I just use 4 commodities for the sake of illustration: wheat, rice, milk, and beef. And let's suppose that the quantities are set to be 20 tons of wheat, 15 tons of rice, 25 tons of milk, and 10 tons of beef. This is all of the commodities that were sold in the base year in a certain small economy. Now the prices of these 4 goods in 2010 were $37 per ton, $56 per ton for rice, $45 per ton for milk, and $75 per ton for beef. So now the total price of this composite commodity in the first year, 2010, will be just the sum product of the first column and the second column, and this is listed as 3,455. Now in 2011, all we need is the prices. So the prices, let's suppose they change to 53, 64, 42, and 86 for wheat, rice, milk, and beef respectively. Now we take the sum product of the quantity column with the 2011 prices, and we get 3,930. And we do the same thing in 2012 and 2013. Each year we need only the prices. The quantities are fixed at the base year quantities, and we just calculate the price of this composite commodity, and that gives us the price index. So it's 3,455 in 2010, 3,930 in 2011, 5,095 in 2012, and 5,910 in 2013. So now we can take the ratio. So this is how much the price index tells us how much the prices have been increasing. So if we take the ratio, we will get the increase in the percentage increase in prices. An index is made by setting the base year to 1. So if these are the prices, 34.55 in 2010, we divide by 34.55, and when we divide that gives us the index in the last row. That sets 34.55 to 1.00. This is sometimes multiplied by 100 to make it percentage points. So the index would be 100 in 2010, 136 in 2011, 159 in 2012, and 190 in 2013. So this is how we calculate a price index. Later in this lecture, we will be working at GDP. We will be working with GDP, or gross domestic product. In current LCU stands for local currency units, and also GDP in constant LCU. These are defined to be the set of all commodities produced by domestic economy in a given year. So basically, the way that we calculate this GDP is to take all of everything that was produced, goods and services, and which was sold, and we evaluate the value of that sale and we add them all up. So it's just like price dot quantity for all of the quantities which were produced in 1 year multiplied by the prices at which they were produced. So it's basically P dot Q over the whole year. In the local currency, that means that if you are in Pakistan, you use rupees. If you're in Australia, you use Australian dollars. So that gives you the current LCU. Then you want to change the current. We will discuss this issue later. The current LCU units have both price effects and quantity effects, and we want to isolate and separate these two. How this is done and what this means we'll discuss later. To assess the validity of the quantity theory, these are the three series we need. The nominal GDP calculated in local currency units. This is done by standard procedures. Every statistics department, bureau in every country comes up with these figures. This is the aggregate GDP for the whole country, not the per capita one. Then we calculate a GDP deflator. This is a price index for the GDP as a whole. It is calculated by using a base year and fixing a commodity bundle and then pricing the same bundle across the years. So you get a sequence of prices for the same bundle. So this shows how the prices have been increasing. Now, this price deflator is not the same as the consumer price index or the inflation index that's commonly available, because the consumer price index refers only to the commodities which matter for consumers, whereas this GDP deflator matters for all production. Some production is for government, some production is for other firms. So all of this comes into the GDP deflator, which is not part of the consumer price index. Now, once I have the nominal GDP, which is the GDP in current prices, and then I have the rate of price increase, then if I divide the nominal GDP by the GDP deflator, I get what is called the real GDP. It is also called the GDP in constant prices. This time the change in prices has been eliminated by this process of dividing by the price index. So these are the three series that we need in order to calculate the quantity theory of money. Using the price deflator, we can divide the growth in GDP, nominal GDP, into one part which is growth in prices and the other part which is real growth. If you think of price times quantity, suppose that both price and quantity increase, so the nominal GDP will increase due to both of these effects. Now the name of the game is to separate these two effects. So if I look at actual data for Australia, in 2011 we have nominal GDP and we have 2010. If I look at the growth rate, just the ratio of these two numbers is 1.0817, and this ratio means that the growth rate is 8.17%. So that's one calculation. Then we look at the price index. The price index has been calculated separately, and that goes from 100 to 106.15, which means that you have a 6.15% increase in the prices. So the remaining portion, if you have 8.17%, 6.15 is due to price, then the remaining portion is due to the increase in quantity, and that's called the real GDP. So that's 1.91%. Now it's important to note that this is a multiplicative calculation, not an additive one. If you add 6.15% to 1.91%, you will get 8.06, not 8.17%. It's actually the growth rates. You take the nominal GDP, multiply it by the price growth, multiply it by the quantity growth, and you get the new GDP. To assess the validity of the quantity theory, we need to compare the rate of growth of prices, which is inflation, and the rate of growth of the real economy with the rate of growth of money. Now, there are many different definitions of money. In our data sets, we will look at two types of money. One is the standard definition of money, which is also called M2, and the other is a broad money definition, which is called M3. M2 refers to what is normally known as money, while M3 includes some additional things which are quickly convertible to money. The differences are technical and not important for our. The issue becomes much clearer when we convert the quantity equation into a logarithmic form, because the multiplicative effects become additive effects. So here's the quantity equation in product terms. I have M times V equals price times quantity, and this holds for both the current period and the last period. Current period is indicated by T, last period is by T minus 1. Now we can take logs to convert this into additive form. So I have log M plus log V equals log P plus log Q. Same holds for the last period. Now if I subtract the second equation from the first equation, I get, note that the log M minus log MT minus 1 is just the log of the ratio of these two quantities. So this is actually approximately the growth rate of money. Log of, this is approximately the percentage change. That's a property of the log, technical. Now, once I recognize that, then I can write the difference of the two equations as the percentage change in money plus the percentage change in velocity equals the percentage change in price plus the percentage change in quantity. It's useful to have that in a explicit form. If I use percent as a short form for notation for percentage change, which is log M of T divided by MT minus 1, then I can write this previous equation as percentage change in M plus percentage change in V equal percentage change in P prices plus percentage change in quantity. And that's the quantity equation in terms of growth rates. This is an accounting identity. It will always hold for all data sets. That's because we use this equation to define velocity. So the value of velocity is chosen to make sure that this equation holds. So this will hold for all data sets, and this cannot prove or disprove any hypothesis about economics. So now how do we get from this accounting identity to an economic theory? Well, we make some assumptions about these quantities that we have defined. First, we say that the velocity is exogenous. How the speed at which money circulates doesn't have to do with the real economy or with money itself. So it is a variable that is not affected by the others. At the same time, we also assume that money affects prices but not quantity. This is called the classical dichotomy, and this leads to the famous saying that money is a whale, or that money is neutral in the economy. So money affects prices but does not affect quantities. So there are two forms of this classical economic theory. One is that it always holds in the short run and in the long run, and the weak form is that it may not hold in the short run. In the short run, changes in money can affect quantities, but in the long run, the effect of money will only be on the prices. As opposed to this, Keynes said that money is not neutral in the short or the long run. So in the later lectures, we will discuss how this works for real data sets and assess whether or not this is true.